Hello, and welcome back to Calculus Coronavirus Edition. I just realized that my microphone was turned off, so my college algebra video has no sound the whole time. That's going to be spicy. All right. Let's talk about section 4.5. 4.5 is a massive step forward in terms of our ability to integrate. So far, in this text, we've only really discussed having some really basic control of integration. We can integrate very specific functions that match to functions that we could differentiate with. This is the opposite of how we've had it handled with derivatives. Because with derivatives, we had a bunch of rules to assist with more advanced functions, right? The power rule and the addition subtraction rule were two of the most basic things. And it turns out these are the same rules we learned about with integration. We can undo a power rule, we can undo addition and subtraction by treating them separately. But in derivatives, we had three other rules: product rule, quotient rule, and chain rule, which allowed us to solve much more advanced problems much faster and easier. As it turns out, there's not a great crossover way to get back. Like, it's very easy to see that we can undo the power rule just by seeing how to get from part A to part B. We can go and take a step backwards to opposite and undo the derivative with an integral, and same with the addition subtraction rules. But since these often can be simplified versions of each other, it is much more difficult to go from this side back to over here taking an integral, or from this side back to over here. This product and quotient rule are very, very, very difficult to integrate. We'll eventually, in the next chapter, talk about something called integration by parts, which allows us to do this. But, oh my gosh, is it a pain. It's hard. And that's coming from somebody who loves this stuff and looks forward to doing it every single day. Like, it's not fun. However, this bottom one, the chain rule, actually does have a nice way to undo its operation. If we can take a derivative with the chain rule, allowing us to take this function f of g into f prime g times g prime, we can actually go backwards using something called a u substitution. It allows us to take this function and work backwards to get back to the original, essentially undoing the derivative and undoing the chain rule. Now, before we can talk about any of those things, we need to make sure to take us time to discuss some ideas from this chapter, specifically this theorem. So in your textbook, page 297, I want to point out Theorem 413. Now, Theorem 413 has a couple components to it, and it's really drawn out, but the big one I point out is this bottom piece. So let's start at the top. Let g be a function whose range is an interval I, and let f be a function that is continuous on I. So in other words, g needs to be a function that has a defined values to it, called an interval, and let f be continuous on the interval. So there can't be any gaps in f on that interval. So there could potentially be gaps in g, okay? But there can't be any in f, because f is the one that's going to be doing a lot of the playmaking. Now, if g is differentiable on its domain, f is an antiderivative on f, then on I, then this process is true. Notice that this piece in here is simply the chain rule of this piece out here. If you were to take the chain rule of the right-hand side, you would end up with the inside of this integral. And thereby, these two happen to be antiderivatives of each other. So in other words, this Theorem 413 is how we undo the chain rule. However, I want to point out that down below is an alternative version of 413. This is what I like to call 413A for alternative. What it's done is everywhere there used to be a g of x, it's replaced with u. And everywhere there used to be g prime x dx, they replaced with du, which actually kind of makes sense. If you take the derivative of this side, derivative of u would become du, derivative of gx would become g prime dx. So these two actually make a lot of sense. And you'll notice that it creates this new, much simpler and much cleaner version of the top formula that has to have these components in order to make it work. And if you were to back substitute into this function, you will find it gets the exact same result. Because if you plug in du is equal to this thing, and u is equal to that thing, you will end up right back here. And if you take the right-hand side and plug in u for g of x, you'll get right back to the right-hand side. And so these two are equivalent statements, but one is written with something called a u substitution, meaning it has taken a nasty function and replaced it with u, which is much nicer and cleaner, and as it turns out, much easier to work with. Now, how does it do this? For our first problems, we're going to actually be doing this process directly. We're going to attempt to find a g of x inside an f of x that contains its derivative. And that process is listed out here in pink in the text at the bottom of page 297, listing out and saying, okay, we are going to take time to identify, okay, what's the f function, what's the g function, what's the g prime function, so we can then take this process and find the antiderivative, or integral as we call it. You have to spend time getting used to finding these functions in a problem, and that's what we're going to do first. We're going to look at a bunch of examples with this. I'm even going to make up a few of my own, but in the meantime, let's talk through a couple. Okay, first example, right here. We have the integral of x squared plus 1 squared times 2x dx. So, the integral of x squared plus 1 squared times 2x dx. So, what's the pattern? Well, this is going to be my g of x. It's the inner function. Well, the reason I know it's going to be g of x, because right here, I have g prime. What's the derivative of x squared plus 1? 2x. So you can see I have g and g prime clearly defined. The next thing comes, well, where's f? Turns out f are these parentheses, which contain a square. So you can clearly see we have an outer function and an inner function, where in this case, my g of x is equal to x squared plus 1, and my g prime of x is equal to 2x. If we use Theorem 413 as a guide, we will actually be able to perform a simple substitution and solve this problem. So, to do this, in order to use Theorem 413 requires us to know capital F, the bigger function, which means we need to find out, okay, we have g and g prime, we have f, we need to find capital F. Now, little f is just the square function. It turns out the square function, if I have something squared, how do I get rid of that with an integral? Well, it becomes something cubed. This is the basic application of the power rule, where little f is something squared, so big F is 1/3 something cubed. It's the opposite of the power rule from up here. This allows us to take our function and modify or change it so that it has all of these different properties. So what I've essentially done is I'm ignoring the g, what's inside of it, because it's not really important right now. Because you notice this pattern allows me to take this step. It allows me to take this shortcut, where instead of looking at the entire function as one big problem, I see, oh, I have a g of x and a g prime, so I can just look at the outer function, because it matches to the chain rule, where we have the outer function's derivative times the inner function's derivative. Well, let's figure out the antiderivative. It's going to be 1/3 x squared plus 1 cubed plus c. How do I know that? Theorem 413. Theorem 413 states that if I can see this particular pattern where I have an outer function defined as little f, an inner function defined as g of x, and an outside function defined as g prime, and this, too, are the big ones. There has to be an outer function, g prime, and an inner function of g, which I've labeled here as x squared plus 1 and 2x, because they are x squared plus 1 and 2x. As long as I have that, I have this really cool property, which states that anytime you have this derivative, according to Theorem 413, we can essentially ignore these two components of it and just integrate the outer part of that function. And when I integrate the outer part, I get 1/3 of that function, leading us here. How do I know this worked? Like, Mr. Douglas, this seems silly, like you just pulled some magic out. Well, I can actually take a derivative and prove that what I did works. So we take the derivative of this function we just found. And if what I did was correct, then when I'm finished, I should end up with the exact same equation as what I started with inside of the integral. It turns out it works like a charm. If I take the derivative of this function, I would have to take the derivative of the 1/3 x squared plus 1 cubed plus the derivative of c. Now, for this one, I would use the power rule with the chain inside of it. So 3 times 1/3 would make the 1/3 disappear. The inside stays the same. Drop 1 from the power. Times the derivative of the inside. The inside derivative of x squared plus 1 is 2x. And the derivative of c is just 0, which you'll notice is the exact same equation. So I know what I did here worked. It has to work. But it works because it fits in this very, very specific form. It is a chain rule that we have simply performed in reverse. So the question is, okay, you see it this time. I've pointed it out. How do you see it next time? Well, you have to look for it. You have to look for inner functions and outer functions. And you might be looking at me and saying, well, Mr. Douglas, couldn't I have just squared this and then multiplied it by 2x using, say, the perfect square formula from Algebra 2 in college algebra, and then multiplied it by this using the distributive property? Yeah, you could have. But the higher this number gets to, the less you want to do that. If this had been x squared plus 1 to the 50th power, you're not going to sit there. I do not believe I've ever met anyone who wants to sit there and find that thing foiled out. Just doesn't happen. And so this allows us to take this function and find these solutions much faster and easier by seeing a pattern. What I am given is the chain rule, and I'm asked to undo it. So how do I undo it? By undoing the chain. I have to be able to look at this piece of that chain function and see, how do I go from here back to where I started? So in other words, I have to be able to look at this function and say, where's the f prime? Where's the g? Where's the g prime? How do I go back? Because if I can find f prime, g, and g prime, I can use those components to get back to the original function, which is what an integral is supposed to do. So all I can tell you is it's going to take some practice. And that's what I plan on doing for the next few minutes, is just practicing this process, because this is not easy. Once you get this thing down, though, you will be leaps and bounds above anybody who doesn't have it. Because if you can look at a problem and be like, oh, use substitution, I can do this, step, 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 done, Theorem 413 is easy. If you can get to that point, oh dear Lord, you will be better than 99% of all calc students. Because if you're just not seeing the pattern, these problems, it gets to the point where they're impossible. You just can't do them. And will somebody who can use Theorem 413 and use substitution will be busting them out like nothing. And if you're in the other category, it gets fun. It gets real fun. Okay, let's look at some more examples. We're working through a few of them, so make sure to follow along. And each one of these, I'm going to follow some steps. I'm going to make it my goal to see how can I find f, g, and g prime so that I can then take the antiderivative and get to my solution. If I can take those processes and steps, I'll be able to figure out where my answer is and how to find it. Let's look at the next one. Okay. Okay. Integral. Cosine Oh, sorry, there's a 5. Cosine of 5x dx. Okay, if you're doing basic rules, you're looking at this problem going, it can't be done. It simply cannot be done. There is no way to integrate cosine of 5x. Now, what we can do is, if we think back to old rules, like we could move the 5 outside, and you have the integral of cosine of 5x, because remember, constants that are being multiplied can be moved to the outside. But then you have cosine of 5x. There is no basic rule of integration that can get rid of cosine of 5x. We can get rid of cosine, but not cosine of 5x. And so now it becomes, do you see it? I have cosine of 5x. 5x is my g. 5 is my g prime, which makes cosine the f part of this function. So we can see here that my cosine, my g of x, is 5x. And the derivative of 5x is 5. So I got g of x, I got g prime of x, and I've got an outer function, cosine. So my f is this cosine function. So the question becomes, well, what's capital F? Well, the integral of cosine is just sine. Remember, sine becomes cosine when you take a derivative. So when you integrate, cosine becomes sine. Okay, so that tells me capital F is my sine function. But now I have to undo the entire operation. The integral of this function, the 5 is part of g prime. Remember, according to Theorem 413, it states that what's going to be left behind is big F with g of x inside of it. So sine with g of x inside of it, and don't forget the constant of integration. And again, I can always tell if I've done this right by checking my work. What happens if I take the derivative of sine of 5x? Well, derivative of sine of x, you do the derivative of the outside first, so sine becomes cosine. The inside stays the same. Times the derivative of the inside. Derivative of 5x is 5, and the 5 would move out front, which you'll notice means they're the exact same function. So I know this process worked. I don't know how else to say it. You gotta see it. You've got to start looking at the problem like this and asking, okay, I have a bunch of different ways I can find it the old-fashioned way, but what new information do I have? What new components do I have to get me to this point where I can look at a problem like this one and say, I can't do it unless I look at it as a chain rule, in which case I can undo it to get back to the original function. Okay, not enough examples. Here are the better ones. Let's look here. We're going to do all 6 of these, one at a time. And the big one is that we're going to talk about is how do we spot the derivatives? Okay? So we're going to look for where's the g of x, where's the g prime, and where's the f. 3 components to each of these problems. And this is actually the first piece of your homework assignment, is to be able to do this, where it doesn't ask you to solve, it just says, can you find the components? Let's talk about part A. For each one of these, I'm going to ask 3 questions. What's the g function? What's the g prime? And what's the f? For each one of these, okay? So for A, we have the integral of 2x x squared plus 1 to the 4th power dx. Well, my inner function is x squared plus 1. My g prime of that. So what's the derivative of x squared plus 1? Well, it's 2x. And is that in the problem? Yes. Note that these two I can spot both ways. I can try to find g first and use that to predict where g prime is. Or I can try to find them both at the same time and verify them in the problem. Okay, if this is g and this is g prime, what's f? Well, in this case, the f is that 4th power. Again, you have to look at a problem like this and see, okay, I have an inner function, x squared plus 1, whose derivative is in the problem. But there's an outer function in the way. This tells me I can use Theorem 413. B, same process. Integral 3x squared of x cubed plus 1. Oh, that should be a square root. There we go. X cubed plus 1 dx. Okay, where's g? X cubed plus 1. What's the derivative of g? 3x squared. Is that in my problem? Yeah, it is. Boom. Okay, so what's the f function? The f function would be the square root, which we can rewrite later if we need to. Again, we have to look at a problem like this and say, okay, where's the g? Okay, where's the g prime? Where's the f? G, g prime, f. G, g prime, f. C, integral of secant squared of x times tangent of x plus 3. The cool thing about this is you can take it a step farther, where your f becomes pretty useless. Ready? All right. This case, I'm going to choose tangent of x plus 3 to be my g. Notice I include the plus 3 because the 3's derivative isn't going to do anything when I do g prime. So what's the derivative of g? Well, the derivative of tangent is secant squared of x. And lo and behold, that's in my problem. Okay? In this case, we have g here. We have g prime here. The question becomes, where's f? Turns out f is multiplying by 1. Doesn't really do anything. Or you could think of it as the power of 1. That's the better way. It's this thing to the first power. Because when I integrate, it's going to raise this from a power of 1 to a power of 2, which is really key. Okay, D. E and F. If you're doing this on your own, you're welcome to pause at any point in time and ask yourself some of these components, because they're really helpful. Okay, for the second part. Theorem 413 is amazing, but it's also kind of limiting, because there's some things that end up being a problem if they don't perfectly work out. Take a look at D. We have the integral of x times x squared plus 1 to the 4th power dx. Okay, well, if I look at the same examples to number A, or letter A, I would want x squared plus 1 to be my g function. But g prime, if I take a derivative of x squared plus 1, I would get 2x. This is the problem. Because we want 2x, we don't have 2x. We have just x by itself. But you notice that the only difference is there's a constant. This 2 is in there, and that's not in my original. We're actually going to talk in a moment about how to fix that. If there ever is, the only problem is there's a constant either missing or it's the wrong constant, it turns out there's an easy way to fix it. But otherwise, this is pretty dang good. With the exception of the constant, everything's good. The only issue is that 2, and well, as it turns out in a second, we can fix it. E, same problem. We have x squared times the square root of x cubed plus 1 dx. We do x cubed plus 1 as our g. We have 3x squared, which is a problem, but the only problem is the constant. So that's really not that big an issue. And then the square root is the other part of it. And then finally f has the integral of 2 secant squared x times tangent of x plus 3 dx. So again, we choose what's inside the parentheses to be our g. This is a pretty common choice. Okay, and if we do that, the derivative of tangent is secant squared, which This one is a problem for a totally different reason. We're missing the number. Okay, this one has a 2, this one doesn't. This one has a 3, this one doesn't. And so it's a different problem. But in this case, in all 3 of these, we're off by a constant. So it turns out we can fix this. All right. Before I go any farther, let's reiterate Theorem 413, how it works, and how we can use it to solve these problems. Okay. Notes. First, remember these are the old rules for derivatives, which, remember, a derivative and an integral are opposites. So if we can do a derivative, we should always be able to undo to get back to the original. Well, with product and quotient, that's really difficult because these can be simplified quite a bit, and therefore it's not always easy to go back and forth between them. However, the chain rule can be gone back and forth pretty effectively using Theorem 413. Theorem 413 is in our textbook. Make sure to take a look at it. It involves seeing the function as a chain's result, f, g, and g prime. F, g, and g prime. As long as you can take the integral of the f function, you can integrate the entire function. And that's a big deal about Theorem 413. If we can integrate f, then we can integrate the whole thing. But it has to be in this form to make it work. That's the big detail. If it doesn't match the form of Theorem 413, and this, we don't get this. This doesn't apply. If it matches Theorem 413, then as long as we can integrate f, we can integrate the entire thing. So when we went to this example, we can integrate something squared. 1/3 that thing cubed. We can integrate, cosine. That we can integrate into sine. We can integrate something to the 4th power. So as long as we can integrate every single thing on this side, we can integrate the entire function, no matter how crazy or nasty it may look at the start. If we see it in this form, we can integrate the whole thing. Okay. That was a lot. Let's go ahead and talk about this rule. In those previous examples, it's much harder to recognize the problem or recognize the pattern because you don't have this component, this piece. And so I want to look at example 3 to see how we can modify very slightly a given problem to force it to be in this form so we can use Theorem 413. And to do this, I'm actually going to look at part D. Now, in the textbook, it uses a slightly different example. We'll go and do the textbook example after this one. But I want to do D to showcase exactly how we do the problem we have here. So I'm going to rewrite D on my next page and show how we can use a constant to fix this problem. Now, in the previous problem, D was the integral of x times x squared plus 1 to the 4th power dx. Okay. So, we already said we knew what g was. We knew what g prime should be. And we know what f is. G, we said, was x squared plus 1. G prime should be 2x. And f should be that thing to the 4th power. Okay, so how do we fix this? We need a 2x out here. We don't have a 2x, we have an x. But it turns out there's a sneaky rewrite we can do. Now this is advanced, but it's so crazy that when you look at it, you're going to be like, well, duh, of course. But until you start to look this way, it becomes really hard to do it this way. So I'm going to make the following rewrite. X is not just x. It is also 1x. That's pretty obvious. But 1 can be rewritten in a whole host of different ways. And one of the ways I'm going to rewrite it is this very special one. This special one is going to force a 2x to appear. It's going to do it by being sneaky. Ready? Here we go. Instead of writing 1x, I'm going to do 1/2 times 2x. All three of these are equivalent statements. We have an x, we have a 1x, and we have 1/2 times 2x. The difference is, this bottom one, if I use the constant multiple rule, you'll notice now can be solved using this form of Theorem 413, which means that the original problem could be solved using this theorem. I just have to see it this way. Notice that this 1/2 is not magical. It's a consequence of rewriting x. X isn't x, it's 1x. 1 isn't 1, it's 1/2 times 2. Causing this 2, which was missing, to suddenly appear. Now, I can't change the problem. X has to stay x, but by rewriting it this way, it would stay x if I distribute it again, which means that this 1/2 and this 2 cancel, giving us right back to the original. But at the same time, by rewriting it this way in particular, I can now use Theorem 413, and I'm going to do so. So how do I do Theorem 413 now? Well, I've got my g prime of x, I've got my g of x, and I've got my f, my little f. So let's integrate. The 1/2 is still a 1/2. It's not going to disappear. But now I integrate what's inside. Well, to integrate what's inside, I need to find capital F. To find capital F, I look at it. It's something to the 4th power. So capital F would be 1/5 something to the 5th power. Right? Using the opposite of that chain rule. In this case, if I take the derivative of capital F, I get back to little f. And so I know this is the right piece. So this is 1/2 times 1/5 x squared plus 1 to the 5th power plus c. So the 1/2 comes from out front. Notice it stays the whole time because it's not being integrated anymore. The 2x was absorbed by the chain. The x squared plus 1 is still inside. The power has changed to a 5. We've added 1 to the power. When we add 1 to the power, we then have to divide by the new power. That's why we get a 1/5 here. And the plus c comes from the constant of integration. And all that's left now is to simplify. 1/2 times this would be 1/10 times x squared plus 1 to the 5th power plus c. You might look at that and be like, what the heck just happened? That's mind-blowing. But I want to reiterate something very specific here. I know this is right if when I take the derivative, I get back where I started. Remember, integrals and derivatives have to cancel. That's the fundamental theorem of calculus, is that if I have one, I can use it to cancel the other. Well, watch me cancel it. I take the derivative. The derivative of c is going to disappear, so this right-hand side piece is kind of useless. But that's okay. Now I take the derivative. The 1/10 is just a 1/10. It's not going to do anything. Now, I noticed that for this piece, I have a chain rule. So I do the chain part. 5 moves out front. Inside stays the same. Subtract 1 to the power, it becomes a 4. I then have to multiply that by the derivative of the inside. The derivative of the inside is 2x. Well, guess what? The 5, the 2, and the 10 are all going to cancel, leaving just an x by itself, and x squared plus 1 to the 4th power, which is exactly what I started with. Wow. That's incredible. we managed to take a problem that was not solvable even by the new theorem we talked about, rewrite it using a trick of numbers, that you may always rewrite a number using multiplication in order to solve it using the new theorem. And it worked. Now, for some of the homework problems we're going to encounter, I'm going to do about 2 more of these. For some of these problems, they're going to be like where you just use Theorem 413, like on this one. Just go. Just do it. And some of them will be more like these, where we have to actually take the time to say and fix whatever isn't working, so we can actually determine which pieces are supposed to be taken out and put back together. Okay, now that this one's done, I'm going to take a moment, stop right here. Okay. I'm now going to do one that's in the text. Let's see. I wish I had another example in the text. Let me do... Let's just do E. Okay. Alright, so this was D. Let's now do E. For E, we have the integral of x squared square root of x cubed plus 1 dx. Okay, so just like before, I know what G is. I know what G prime is. I know what F is. I'm going to add this 4th category over here for later. Okay, G is going to be x cubed plus 1. G prime is going to be 3x squared. My F function is going to be the square root, which is also a 1/2 power. I'm going to rewrite that. And big F, I'll deal with afterwards. Okay, so let's see what we have so far. I have G, that works. I don't have G prime. I have x squared. I'm supposed to have 3x squareds, but I'm going to fix that using the same trick I did before. Instead of writing x squared, I'm going to write 1/3 times 3x squared. This does not change the problem. It just rewrites it. The 1/3 and the 3 combine to a total of 1 when you multiply them. So I still have 1x squared, just like I started with. So I haven't changed anything, I've just rewritten it. But you'll notice that I now have the 3x squared I need in order to use Theorem 413. So I bring the 1/3 out front. Integral 3x squared square root of x cubed plus 1 dx. All right, now I can use Theorem 413. How do I do it? Well, I'm going to integrate those pieces. The 1/3 is still here. It does not go away. If it goes away, that's when you've made a mistake. The 1/3 needs to stay. The 3 is going to be absorbed by G prime, but the 1/3 should still be there because that's what makes it x squared, what we started with. Remember, I should always be able to go back and get back to the original answer. If this 1/3 appeared, it's going to stay. Okay, let's integrate. So, if we do Theorem 413, this would say I need to have capital F next. Now, the integral of 1/2 as a power will become, we add 1 to the power, so I make it a 3/2, and divide by the new power, which would be a 2/3. So, this becomes times 2/3 x cubed plus 1 to 3/2 power plus c. Wow. Okay, so Theorem 413. Theorem 413 states, if I take the integral of something that is in this chain form, then I have to keep the inside the same, but do the rules for the outside. As long as it fits the form, this is going to work. So, g was x cubed plus 1. G prime was 3x squared. F was the square root function, or 1/2 power if you prefer, which I do. And then capital F is where I get the second piece. The integral of something to the 1/2 power is 3/2 of that power multiplied by this 2/3 power. Okay, I'm now going to simplify some. This will become 2 over 9 x cubed plus 1 to 3/2 power plus c. You might ask whether 1/3 isn't being applied to everything. It is. But c is a constant of integration, meaning if I did multiply the 1/3 times c, it's 1/3 times c, so it's still just c, because it's an undefined value. It's not even a variable. It's just unknown. Like, variables are usually things that can change. C is just unknown. It could be anything. So 1/3 c is just a different unknown, so it's still unknown. The c is absorptive in that way. We talked about that before. Break, don't forget. Now, I can't just look at this and be like, obviously this is right. I have to check this, so I'm going to. Now, in your problems that you have tonight, you may skip this step. You may skip checking it. I encourage you to check, even if the problem doesn't say to. The reason I encourage it is because you may make a mistake. You have not done this before. Don't be ashamed if you're making mistakes on something you've never done before. When we all first learned to ride a bike, we fell on our faces, probably got a couple of cuts and bruises. Don't expect that to be different because it's math. Okay, the cuts and bruises are just going to be in your head, and they may last a little longer, so be careful. All right, take the derivative. The 2 over 9 is going to stay 2 over 9. We now have a chain rule. The derivative of this function, we would multiply by the power. Subtract 1 from the power. 3/2 minus 1 is 1/2. Times the derivative of the inside. Derivative of x to the third power plus 1 would be 3x squared. And, lo and behold, watch the magic. 2 and 2 are going to cancel. The 3 and 3 make a total of 9, which cancels with the 9, leaving me with just an x squared times x cubed plus 1 to the 1/2 power. Exactly what we started with. That's how I know this answer is right. There's another example of this in your text. It's right here. Example 3 in the book. Very helpful. And it even goes through and showcases how to find it in different ways. Because, as you might imagine, writing out a lot of these steps is really annoying. Okay? So skipping this middle step here where we use the multiply and divide thing to get rid of that nasty extra fraction, very common to just move that step on. Okay. Last thing I want to mention is right here. The actual formal way to change the variable using a U substitution. I can't express enough how useful this particular function is. To be able to change it to a new function, to a new variable, to make it into one that is solvable. Like this one right here is not solvable in its current form. If you change the rules, you can do it so that you actually get to a new form that's better. We're going to talk about this one next time. This is where we're going to start picking up on page 300. For now, I'm going to go ahead and put a stop. It's Friday. Let's have a shorter day. And let's look at our homework assignment for tonight. We will be picking up when we have the full change of variables with U substitution. So for us, what I would like you to do... Okay, I want you to do page 306/330, depending on whether you're in a book or whether you're in the PDF. I want you to do numbers 1 through 29, every other odd. Not too many problems, but you're going to need to practice. Okay, I cannot stress enough how important it is to practice in this section. Like, every other time somebody says this, like, oh, you need to practice to get good. There's some things you don't need to practice to get good. I'm sorry. You just don't. But this, you will struggle if you do not practice this stuff. Please take the time, take a look at some of these problems, and take a look in the book showcasing how to do some of these, especially using Theorem 413. We will pick up where we left off, looking at the change of variables, so actually performing a true U substitution, and do the second part of the homework then. I look forward to seeing you guys when we get back. That'll be on Tuesday. And I hope you guys enjoy your weekend. Remember, all our things are going to be due this Saturday at 11:59 p.m. And I will be having an open window where people from my college algebra class and the calc class can come together and ask questions. That will be taking place sometime tomorrow. I am not sure when. It depends upon when I'm free. But I'll try to make it a large window so that if you are available at any point in time, you can pop in, ask your questions, and leave. I hope you guys have a good weekend. Make sure you get your homework turned in. And I look forward to talking to you guys next time.